there, astronomy students. This is Miss Ruark. We're in vodcast 16.1, which means we're in chapter 16, and we're talking about the different types of galaxies that there are throughout the universe. All right, so galaxies look like fuzzy little objects when they were looking through 19th century telescopes at them. But as the construction of the telescopes got larger, astronomers could see more detail. I'm sorry, I have the hiccups. Could see more detail and were able to see to show that these were actual galaxies instead of little fuzzy nebula. Okay. All right. So, I'm going to have to get rid of these hiccups because they're going to bother me. All right, so galaxies are star systems. They look like our Milky Way. They contain anywhere from a few thousand to tens of billions of stars. And there's a large variety of sizes and shapes. So galaxy diversity. This picture here is the Hubble Deep Field. It's a 10-day exposure on a part of the sky that we look at and we don't see anything because visually we can't see it. It's too far away. It's not giving off invisible light. Okay, but looking at it through the Hubble telescope, which can now magnify things and pick up different types of radiation, we can see all of these different objects here. Okay, and then here there's a star, and here there's a star. This is a foreground star that would be in our galaxy. Okay, so even though it looks like it's really blank, there is actually a lot of stuff there. Okay, so these large areas that are blank, they look blank to us, but if we take pictures with these really large telescopes, they can gather more light, which means that we can see more stuff. And here is a picture that has been taken over 10 days with the deep Hubble field. Okay, so here's just an example of some of these different types of galaxies. You have your spiral galaxies, which are these with these nice little swoopy arms. And then you have your elliptical galaxies, and you have your irregular galaxies. And here are some that are actually interacting. All right, so galaxy classification. There's different ways that you can classify galaxies. Of course, we saw ellipticals, spirals, and irregulars. And the ellipticals are going to be round or elliptical in shape, and they are subcategorized or classified by numerical index going from 1 to 7. E0, elliptical 0, is going to be more spherical shaped, and E7 is going to be more elliptical shaped. Okay. Remember, elliptical goes more towards like an oval and away from a round circular shape. Okay, then you have your spirals, and your spirals can be classified into a sequence as well. SA, which has a large nucleus, it's tightly wound arms. SB, which is going to be in between, and then SC, which is going to have a small nucleus, loosely wound arms. Okay. Let's come back to this. Let's talk about these some more. So these ellipticals are going to be round or elliptical. They contain little gas and dust, and they don't typically make new stars. They lack the hot blue stars and have a kind of a reddish tint. The spirals are going to contain disks and spiral arms, very similar to our Milky Way galaxy. They all have halos. They might not be visible, but they do have halos. The halos usually lack gas and dust. There's little star formation, and they have a reddish tint to them. Okay, but the actual spiral galaxy itself contains more gas and dust in the disk area, which would be the arms, support active star formation, especially in the spiral arms. Some of them have new massive stars in that are hot and blue, O and B stars. Okay, remember they're hot, they're big, but they have a short life. And the spiral arms will have a blue tint, such as this one here, because, well, the hot gases that are being given off. Okay, so you've got that. All right. We did talk about this. Spirals are rich in gas and dust. Ellipticals have almost no gas and no dust. They're devoid of gas and dust. Galaxies with a disk and a bulge. The ellipticals are galaxies with disk and bulge, but no dust, so they're termed S-zeros. Sad little things. All right, with the spirals, you can have a barred spiral galaxy, and that just means that sometimes it produces this thing. It looks like it has a bar here in the middle. Yeah. All right. 2/3 of spiral galaxies have this pronounced bar structure in the center of them. They're elongated nucleus, which is this part right here, the bar. Okay, and then these spiral arms that come off the sides. Off of the bar. And again, the sequence for these would be SBA, SBB, and SBC, which would be similar to the regular spirals, where the SBA has a larger nuclei, less gas and dust, fewer hot bright stars. SBC would be a small nuclei, lots of gas and dust, many hot bright stars, and then the B would be in between. All right, irregular galaxies, they have no obvious shape. They contain gas and dust. They do support star formation, and they're often the result of galaxy collisions and mergers. Often very active star formation sites. They have starburst galaxies. Okay, and some of them are going to be small dwarf galaxies, which are going to be satellites of larger galaxies. An example of that would be the Magellanic cloud. Ha, I say it wrong every time. All right. How do we measure the distance to other galaxies? Okay, so how do we do that? Well, astronomers have, it should say found, not fun, found the distance using distance indicators called standard candles, and these are objects of known luminosity. Okay, so the most, there's the Cepheid method, which uses the period luminosity relation. Let's see, most accurate distance indicators are Cepheid variable stars. You take the repeated brightness measurements of the Cepheid stars and determine the period of the star, which then can be used to determine the absolute magnitude. Right? And then the other way you can do is a type 1a supernova, collapse of an accreting white dwarf in a binary system. And the type 1 supernova have well-known standard luminosities, and you can compare the apparent magnitudes to find the distances. So both of these would be considered standard candle methods. Okay, you know the absolute magnitude, the luminosity. You compare it to the apparent magnitude and use that to find the distance. All right, so the Cepheid distance measurement. Here, the repeated brightness measurements of Cepheids allow the determination of the period, and thus you can find the absolute magnitude. Okay, and if you know the absolute magnitude, you can find the distance. Okay, so here is repeated pictures: April 23rd, May 4th, May 9th, May 16th, May 20th, May 31st, and you see the star, the brightness of the star, repeated brightness. Okay. Most distant galaxies. So, let's see. Others can be determined. We can use the Cepheid variable stars to determine those that are close. But the ones that are further away, we can't use those. So we have to use other ways to do that. And that would be by globular clusters, planetary nebula, and supernova explosions. Okay. At extremely large distances, the general characteristics of galaxies can be used to estimate their luminosities and distances, because you can't really measure anything else from it because it's too far away. All right. You can also use the Hubble law, and this is brought up by Edwin Hubble. I think it was Edwin Hubble. That was his name. In 1913, and he said, hey, guess what? Distant galaxies are moving away from the Milky Way, and they have a recession velocity, VR, that's proportional to their distance, d. So if you figure out the speed that they're moving away from us, you should be able to find the distance that they are from us. That's pretty cool, right? Okay, so rate of recession is related to distance by the Hubble law, and that's what this says. Okay. V would be the velocity, D is the distance, H is the Hubble constant, and you measure VR through the Doppler effect to figure out the distance. So distance to the galaxies is extremely large, extragalactic distance scale, right? So they're so far away that we can't use parsecs because it's actually too small of a measurement. I don't know if you remember, but when we did all our measurements with the moon and the sun and planets and all that, we said that parsecs was too big to use. Well, guess what? Now when we're talking about the universe and parsecs is too small. So we have to use megaparsecs, and we use gigaparsecs to talk about the distance. Just remember that the distances of megaparsecs or gigaparsecs, this is just light that has left that galaxy millions and billions of years ago. So you're actually um, seeing the past when you view them. When you see those stars in the sky, you're viewing the past. All right. Um, oh, they call it look back times of millions or billions of years. And an example of that they gave was when there's a lag in communication. So if you're watching a TV, like a news report, and they have a news reporter who's on scene somewhere and somebody asks them a question and they sit and they listen for a second and then they answer, that would be look back time. All right, galaxy sizes and luminosity. So galaxy sizes are going to vary. Their luminosities are going to vary as well. Okay, dwarf elliptical and dwarf irregular galaxies are only a few percent the size and luminosity of our galaxy. Ah, they're teeny tiny. And some giant elliptical galaxies are going to be 5 times larger than the Milky Way. So we have small, low luminosity, irregular galaxies, and then we have giant ellipticals and large spirals that are a few times larger than the Milky Way itself. Um, all right, so rotation curves of galaxies. We know that galaxies are rotating around and around. As they're rotating, we can see the frequency of the spectral lines across a galaxy. Okay, and what we see when the galaxy is rotating towards us is the lines are actually going to be blue shifted because it's coming to us faster. And when the galaxy is rotating away from us, the lines are going to be red shifted because it looks like they're slowing down. And so this red shift and blue shift of these lines infers rotational velocity. Okay, so if we take rotational velocity and we put it on a graph and we plot it against the distance from the center of the galaxy, we can actually get rotation curve. And rotation curve, yep. Okay, so rotation curve can be used to measure the mass of a galaxy. Okay, based on rotation curve, this is the most accurate method. It's only applied to nearby galaxies, and we would use Kepler's third law to help us figure out the distance. Okay, not the distance, the masses. Okay, so we measure the rotational velocity due to the red and the blue shifted lines, and we plot it to get our rotation curve. Okay. Let's come back. The other method that you can use to find the masses is if you use velocity dispersion method. This is also known as the cluster method, and it's used to measure radial velocities of galaxies and sizes of clusters. All right, so yeah. Okay, I think that's it, and I'll see you later.